check if it's there. The idea is that sometime today, so if you want to, you can print it out so you can take notes tomorrow morning. So for those who came in later, the last of the 4 blocks, we're going to try to make a transition from two-level analysis to multiple imputation and plausible values. And I think a very good way to make the transition is via meta-analysis. We start off thinking Bayesian alternatives to factor scores, which we will then talk more about, both multiple imputation and plausible values, towards the very end of today. So if you go to slide 151, here's what I learned about meta-analysis. It's an attempt to bring together information from several research studies designed to address the same scientific question. And unlike multi-level data, typically level 1 data is aggregated. You very often don't have the individual data for level 1. Instead, you frequently have summary statistics, effect measures of different kinds, like Cohen's effect measures, mean difference divided by log odds ratios for categorical outcomes, relative risk, could be Z-transform correlations. And instead of having the individual data on level 1, you have an estimate of the sampling variability of this summary statistic. So you get the precision, because different studies may have used different sample size, for instance. So those associated sampling variances are going to be taken as a form of data that we're going to use in the analysis. And here's how it goes. You can read the data varies across the studies, and a variance that varies across the studies. And we're going to assume that the variance, the study-specific variance, is known, estimated from the data. So we're going to assume that that variance is so well estimated we don't have to bring in any uncertainty in the estimation of the variance. And we're going to use a random effects model where this mean in each study is assumed to follow a normal distribution of mean called hyperparameters. So, you know, or hyperpriors. It's like having priors have priors. I don't know how long you can go in that chain, but you have a random effects model, and for those unknowns, mu and tau squared, we're going to add Bayesian priors. So for instance, we have a non-informative prior for mu, mean 0 and a very big variance. So we say nothing really specific about it. And a uniform prior for tau, we're just saying that it's greater than 0, but can be very large. We have very little knowledge about it. So that's a standard setup for a meta-analysis. And we're going to see that that has interesting features. It may at first look a little bit scary, a little bit unknown, but we're going to put it in a very familiar framework, and you're going to feel very comfortable at the end. Here's an example from Gelman's book. Did I mention Gelman's book? It's very heavy too. He has an example on beta blockers. That's supposed to be muscle relaxants for the muscles of the heart to prevent myocardial infarction, heart attacks. And he takes that from an article by Yusuf and others. And it's 22 clinical trials. So one way of thinking about that is that you think we have 22 cluster units. 22 cluster units. capital J is equal to 22. And he has randomized patients to getting a beta blocker and not getting a beta blocker. And he looks at dead or alive. So it's a dichotomous independent variable and a dichotomous dependent variable. And to measure the relationship between those two, we use a log odds. Log of a cross product ratio, the usual Yule type of association coefficient. So the log odds is this difference of logs, which is the log of the ratio of these odds. And in stat books you have an approximate sampling variance that looks like that, and it can be adjusted by adding 0.5 and making it better. But those are the ingredients: a dependent variable y, known sampling variance in each of the 22 studies. And here you have half of the data. On the next slide you have the other half. And I like that aspect of meta-analysis too. You can easily type in the data. I actually did it myself. So here are the first 11 studies, and you have deaths and total. In the control group there were 3 deaths among the 39, 8%. Treated group, 8%. So there the beta blockers didn't do too well. Here, 12% in study 2, and only 6% died as treated by the beta blocker in study 2. And you see how the sample sizes differ across the studies. And these quantities can be translated into so-called log odds that we talked about. And we see that the log odds should be negative for the beta blocker to have a good effect, because then this percentage for treated, the percentage death, is lower than that. So negative log odds is good, but not all of the studies have negative log odds. Here is one with an adverse effect. We don't see it here because of rounding. Here is a positive adverse effect as well. But on the whole, there seems to be some benefit from taking beta blockers. And here is the standard deviation from the sampling variance square rooted estimated for each study. And we're just using the data from the last 2 columns here. Here's the last 11 trials. And it's interesting how this ties in with various things that we know about. First of all, if you think about single level modeling, there is a way to handle heterogeneity or heteroskedasticity. Heterogeneous variances show heteroskedasticity. Think linear regression, meaning that, for instance, as x increases, the residual variances increase like a fan, like this. That can be handled by random slopes modeling. We have a user's guide example 3.9, random coefficient regression it's called. It's popular in econometrics, and it's a way to allow for heteroskedasticity. You may want to take a look at that. We actually, Timur and I explicated that in a web note number 3, how to handle heterogeneous variances. So that comes in handy here because each study of the 22 studies has a different variance. So we're going to draw on that trick. And it turns out that Mike Cheong, I think he's in Singapore, had a similar approach used in the Psych Methods article, which is a nice overview article. I recommended that in my email to you. Integrating fixed random and mixed effects meta-analysis into structural equation modeling. And the idea then, once again, if you write out what I had on the previous slide, the formulas I had, you have y equals theta j plus a residual. This is the effect in study J, but with a certain variation around it, where the epsilon is assumed to be normal sigma square j. So this is the same theta and sigma square that we talked about before, except now we've written it in a linear regression-like equation. Now what you can do here is divide both sides by the standard deviation of this known quantity, sampling variance of the study J. And you will get a y star j, which is y divided by sigma j. And instead of theta j, you get theta j times xj, where xj is simply 1 over sigma j. And where you can add a 0 intercept just to mark that that is really 0. That was an invisible 0 here. And where the residual is normal with mean 0 and variance 1, because you have divided by the variance here. And theta j is still a random slope with these hyperparameters mu and tau squared. But once you put it into this form, it's easy to translate it into Mplus. So I wish we had 2 screens here. You could see the formulas falling right into the input for Mplus. Here I'm showing it for maximum likelihood, single level. You do a type equals random analysis. We have transformed the y by dividing by the standard deviation, which sits in the data. And we create an x variable, which is created in the analysis as 1 over the standard deviation. We fix the intercept at 0. That's what the formula showed us on the previous page. We fix the error variance of y to 1. We define a random slope. Theta is a random slope for y on x. And we have to go back now. Theta is a random slope in the regression of y on x. It's random because it varies. And the way we do that in Mplus is to have that bar statement. Theta is the random slope variable in the regression of y on x. And then theta is the variance of theta, namely tau squared. And bracket theta is the mean, namely mu. So this would give you ML estimates for this example. Now you can do this as 2-level modeling too, and it may be more intuitive, pedagogically intuitive. Still for ML, you say then that you have 2-level modeling, and on the within you have the same thing, and you have the random slope y on x, but you, instead of having a single level now, you put the random slope variance and mean on the between level here. So this is perhaps more natural because you have here how many clusters? You have 22 clusters. So you should write there 22 clusters. And how many cluster members do you have? 1 in each cluster. How can you estimate variance on within and between if you have just 1 cluster member? Answer is you don't. You have the within variance fixed. This is what Raudenbusch and Bright called the V-known case of multi-level regression. So the variance is known and on within, and you estimate it on between. So you should think of it as a 22 cluster problem where each cluster has 1 member, but you have known within variance. I mean, at least that's how I like to conceptualize it. Because then that translates to when you have data beyond the summary statistics on the within, when you have the raw data on within, then that will be a multi-level analysis. So why not begin there? And you get the estimated mean of theta, the log odds effect mean across the studies. It's beneficial to have the beta blocker, and it's variance. But that's ML. Now if you go to base, you do the same transformation divided by the standard deviation of each study. 2-level random estimated base. Fixed base iteration of 10,000 to make sure the posterior is well captured. To not be bothered by autocorrelations, although we've told you they're not too serious. You can thin it out to take every 30th draw iteration, which is slower but avoids high autocorrelation. You can switch from the default median to the mode instead, which may be what we should do according to Brown and Draper's article when we have a small number of clusters and use a uniform prior. Right? That's what the simulation showed. So mode goes together with that prior, which sits here. And otherwise, the within and between study parameterization and language is the same as before. So quite simple. Quite simple. And here you should expect now to get the same results as in Gelman's book. So we have the answer. And here's what you get. You're not interested in the within level. You don't estimate anything there. Everything is known. What you're interested in is simply the mean and the variance of theta. The study-specific effect has mean minus 0.255 and variance 0.013. Now we're going to see what the posterior distribution looks like for theta. So this is the between study variance of theta sub j. Again, a very chi-square-like distribution, right? But it comes down a little bit here, so it has a peak that's positive. So mode is positive, and the median is positive. And the median and the mean are not too far away from each other. But this would be a reason for not using ML, where you assume approximately normal parameter distributions. So now let's think about how to interpret the effects. So we saw that the estimated mean for theta, which we call mu, is negative 0.255. And for the mean, we have a Bayesian posterior 95% credibility interval. Goes from minus 0.386 to minus 0.092. And that's in the log odds scale. So we might want to exponentiate it into the odds ratio scale, 0.68 up to 0.91. And the fact that it doesn't cover 1 means that it's the results are in favor of using the beta blockers. The odds ratio is less than 1. It doesn't cover 1 here, that therefore it favors the beta blockers. So maybe not a strong effect, but the lower endpoint of that credibility interval would indicate a fairly strong effect, but an important effect probably, nevertheless. Now, in contrast, what you could do is just add all the 22 studies together, pool all of them, which means that you assume that they are all identical, so that there is no effect variation across studies. That is, you're implicitly saying excuse me, that the variance is 0, for which we saw positive results in the base analysis. But if you assume that the variance is 0, so treating all studies as being the same, you will get a narrower odds ratio interval, 0.70 to 0.85. So a higher lower end and a lower higher end. But that is artificially too low, as Gelman argues for in his book. And the Bayesian approach, allowing for an across-study variance, is the better way to go. So we estimated the variance by the mode because of the use of that particular prior. So the mode is tau square 0.013, which says that tau square may be very close to 0, as we see in the posterior, looking at the 95% credibility interval, but may also be plausibly, as Gelman says, as high as 0.14, standard deviation 0.38, if you take the higher end of the 95% credibility interval. So that's a way to summarize several studies, allowing them to vary in results, but borrowing information from other studies is what we're doing is making a so-called exchangeability assumption across the studies here. What's interesting, though, is that we can now estimate from this model, we can estimate the study-specific effects. You know, we had the observed effects Y, but are the true effects? That's what we call theta. And I think the easiest way to think about theta is as factor scores. So we want to estimate. So this is like, think about a study in schools. Students within schools. You want to estimate the school-specific random intercept. That's like a level 2 factor score. So now you have the study-specific theta effects. You can estimate them for each of the 22 studies. And they are latent variables. And in Bayesian analysis, and here's your first encounter then with plausible values. In Bayesian analysis, you can create these factor scores in 2 steps. First, you take a random draw of the mu and tau square values from their posterior distribution. You have now found the posterior distribution. Now you can take a random draw from that. And second, then, once you have those, you can draw theta from the theta distribution, which has mean mu and variance tau square. So first you draw the parameter values, and then you draw the data points, so to speak. That is a plausible value. And you do that many, many times. In this case, here's how you do it in Mplus, data imputation, which Thierry will talk more about. And we do 100 draws. So think about factor score for one person or factor score for one school. We're going to get 100 values for that one person's factor score. We're going to get a whole distribution. And we can save those values, all 100 values of each theta j, in save equals this data set. And we get some summaries if we have the plausible equal option here as well. Giving summaries like mean, median, and percentiles. And you will find then that the plausible values are shrunken toward the overall mean, mu, with stronger shrinkage for smaller studies. So if you look at it here, what we've done is we've added the last 3 columns. That's the posterior for theta j. That's the from the plausible value distribution for theta j. So for instance, if you take a fairly small study, like study 6 here, 52 and 59 people, the log odds was fairly large negative compared to the others, right? But since the mean is smaller, it will be shrunken towards the overall mean. So the estimated effect from drawing information from the other studies is going to be smaller for that study. See what I mean? We've shrunken it. We've changed this estimate, which only uses information from study 6, to minus 0.280, which is using information from all the studies. And let's see, the study here, the first study, that actually got a adverse effect of beta blockers, a small adverse, is changed into a positive effect by drawing information from the other studies. So that has to do with shrinkage and Stein estimators, I guess it's called in statistics. But it also has to do with factor score estimation and plausible values. So what we're doing here is 2-level analysis. And you can think about this as a way to, if you want to, in 2-level analysis of students within schools, you can actually, these values are the school value for the random intercept, for instance. That may be of interest to see if a certain school does better than expected. You could probably evaluate teachers with it too, if you want to be controversial. I'm not going to go through these slides in interest of brevity, but on the last couple of slides, I show you how meta-analysis can be done with a covariate. So for instance, studies are assumed to be exchangeable, but you could bring in information about how they differ in meaningful ways. For instance, as Jules Parks uses an example in his multi-level book about study interventions that have a different duration. So the length of intervention is used as a covariate. Number of weeks here is covariate for the study, showing the duration of the intervention. And by the way, if you want to play with these data sets, I'll be happy to send them to you. But these data are also easily typed in, not very many. And anyway, so he has week as a covariate, and these two slides show you how you can bring in covariates in this analysis as well in the Bayesian fashion using two-level analysis. So there you have it.
All right, my turn. So I'm going to talk about multiple imputations now. So can I ask you guys if you have done multiple imputations? Anybody? With any program? Wow. All right. 30%. Yeah, that's great. Okay, so multiple imputations for Mplus came out in version 6. We had a little bit of a bumpy start, I guess, until we figured out how to do the covariate correlation matrix. 6.1, much better, much easier. So that's and now pretty much single level or two-level imputation works really well. All right, so I would just go over a little bit of missing data concepts. There are several types of missing data. Just in general, why do you need to analyze? Why do you need to have capabilities to analyze data sets with missing data? It's just because this analysis, if you throw away all the observations that have some missing data in them, you reduce your sample size a lot. So generally, you want to have capabilities to deal with missing data. The three types of missing data that we'll consider now. So missing completely at random. This is the very simple missing data type where variables are simply missing by chance, or they come. The missing data comes out of a randomized design where you randomize the subjects into getting one test or another test. Another example is with multiple cohorts where you actually model it as a single population, and and you have to enter missing values for certain longitudinal models for the different cohorts. Then you have missing at random, and that's basically where most of the analysis occurs. And basically, you want to have capability of handling this type of missing data. So here, missingness is related to an observed variable. So you can have an observed variable kind of be a predictor for the probability of the variable being missing. This can also occur for example, in these selective designs where just by design, certain types of people have missing data, and that also can lead to basically an observed variable, such as say race, be related to what missing data you have in your data set. And finally, this is the most difficult type of missing data, with non-ignorable missing data. The missing at random is basically handled correctly by any likelihood-based method. So most statistical methodology chases this. Some more advanced methodology would attempt these methods also. And Mplus is actually a pretty good tool to model non-ignorable missing at random data. But here, basically, the missingness is related to values that are missing. So, and the other possibility is that the missingness is related to latent variables, which are also not observed. And that basically means that this missing data is not MAR. So So we have these three types. And basically, so again, we are basically after this condition, missing at random. And one way to actually make this assumption more plausible is to use all the data you can collect, all the data in your data set, because you don't know whether some of the variables in your data set might be somehow related to the missing observations, and might be helpful in predicting these missing values and recovering these missing values. So generally, you want to include, in missing data analysis, you want to include all the possible variables that you think that might be somehow connected to the missing data. At the same time, when you include all these large number of variables into the missing data analysis, you might not want to include this into your models. The models actually might be some structural models with some causal effects, and if you keep on adding variables that you have, just to guarantee good analysis of the missing data, you end up with a huge model that is going to have a lot of parameters, and if you add variables, eventually you're going to reduce the precision of the estimates as you get. So it's better to keep the model that you estimate as parsimonious as possible. So just keep the variables you really want to analyze, but somehow include the entirety of your data set to take care of the missing data. So that's basically a standard methodology, the standard approach of dealing with missing data. So, and we'll feature basically two different ways to deal with that. One of them is the Bayesian method, and then the other one is this command that we have in Mplus, is basically to add auxiliary variable with auxiliary, and then you list the variable names, and you put bracket m. And that's what Mplus will do in that situation, is we'll use a maximum likelihood analysis, and it will basically correlate all these auxiliary variables with all the observed data, and thereby analyze the missing data. At the same time, they're not going to be put into the model, so the model is going to stay small, but you're going to use all your data, all the auxiliary variables to actually predict the missing data. So that what is the name of that article, Bengt? Who was the? There was the same article that.
By John Graham.
Yeah, John Graham. So that was a same article maybe about 5 or 6 years ago, that featured this methodology, and it's implemented in Mplus. What we're going to talk about, this is the new stuff that we've implemented, is the multiple imputation stuff, which is probably a lot more common. I think it would be a lot more common in general.
It's also written about by Craig Anders, and he has it all very nicely summarized in his book at the bottom there.
Yeah, and this reference is at the back of the slides. Basically, multiple imputations is going to handle the same problem by conducting the multiple imputation on the entire data set, including all the variables, into the missing data analysis, and then you can select a subset of your variables to actually make a model for them. So that's the approach with the imputation method. And multiple imputation is basically done using the Bayesian methodology. We first estimate the model. We wait until that model converges. After it converges, after we conclude that it converges, we continue to draw parameters from the MCMC sequence. And those are the parameters from the posterior distribution. And from those parameters, we generate missing data according to the model. And those these are basically done to ensure that the imputations are independent. We take about 100. We take exactly 100 iterations between every imputation. So that's Mplus default. And basically, what we want to point out here is that this step one is the model that you choose to impute the data is is where the flexibility is, and you can choose different models. You can choose an unrestricted model, which we call H1 imputation, and that usually means just a variance-covariance matrix. If you have categorical variables, it's going to be a correlation matrix, tetrachloric correlation matrix, polychloric correlation matrix. But basically, it's a saturated model, basically, that we would use for to model the entire data set. Another possibility is where you can actually use a restricted model. You can use a model that you can actually write into the input, just like you analyze any other Bayesian, any other model with a Bayesian analysis. You can actually write the model, have Mplus estimate the model, and from that model you can impute the data. And for example, you can. There's two main reasons why you would want to do that instead of such an unrestricted model. So, if you're sure that your model is correct, you can actually obtain more accurate imputed values if you use, that model. It's and the second reason is why you would want to use H0 more restricted model is if there is a problem with the unrestricted model. So this model has huge number of parameters. If you have 100 variables, this thing is going to have 5,000 parameters. So this is a huge number of parameters that you're going to have to estimate. Naturally, you might run into problems with this kind of estimation. And H0 imputation actually offers an alternative. You can basically use a one-factor analysis model, or if appropriate, a growth model, or something that's a little more tractable to impute your data and feasible. And then you also have this possibility, latent class model. So latent class model is a totally new animal in a way, because look, factor model and growth model, they're basically the same as this model. I mean, you have structured variance-covariance matrix here, right? And here you have unstructured variance-covariance, but it is the same thing. It's a variance-covariance matrix. When you do imputation with latent class model, you actually have, it's not a linear model. It's just, a mixture of different things, and it can actually be, you can gain some tremendous benefits out of a imputation like that if you think it's appropriate. So, and that depends on the application. And also you have the, two-level imputations. So, basically the way you do the data imputation in Mplus, there is a data imputation statement, and it has a few options, not many, 3 or 4 options altogether. One of them is the model option. And this actually option is when you use H1 imputation, when you use unrestricted model imputation. So we have 3 different saturated models to choose from. This one is basically the one that I just talked about. It's basically an unrestricted variance-covariance matrix. Or if you have categorical data, it's going to be a correlation matrix or a mixture of the two. Just polychloric correlations if you have both categorical and continuous. And that's our default. Lately, as I was saying before, we've figured out a much better way to estimate the correlation matrix, so we don't really get much problems nowadays with this. But still, you can still run into a lot of estimation problems. If you have a huge data set, you're going to be estimating a huge model, and Mplus will not impute anything unless the model has converged. So that means that you really need to have a converging model, and the reason that's why we actually implemented all these 3 different saturated models, because in certain cases you might actually run into problems with one of them. So let's move to the sequential saturated model. This basically model came out of a Gunatan paper, and it's implemented in some other software, which I can't remember the name right now. But which one? IBWare, yeah. Basically, in fact, actually, this was our default in version 6, and we kind of did like that model before, that was more robust. But now, actually, this model is more robust because we improved the estimation. So that's our default for all the imputations. And this one basically is regression. You sort of sequentially regress. If you have 100 variables, the first equation is you regress the second on the first. The second equation is you regress the third on the second and the first. The next equation is you regress the fourth on the first three. And keep on going like that. So it has the same number of parameters. The main difference between this model and this model is that when you have categorical data, here in the equation, in the regression equation, you actually you use the observed value being 0 or 1 if it's a binary variable. But here you always work with the underlying continuous variable. So that's essentially the difference between these two. And finally, this regression method, it's also fairly useful. It splits the variables into variables that are missing and those that are not missing. And the ones that have no missing value become covariates, and they have nothing estimated in them. It's all conditional on those. So in certain cases, this model can also be useful. And all the details are in this technical report on our website, so everything is pretty well documented. So plausible values. So what do we call plausible values? These are basically the imputed values for random effects. They're part of the H0 imputation that I mentioned before. Again, H0 imputation is nothing more than estimating a model with the Bayesian estimator, and after the estimation, you keep on running it a little bit longer to impute everything from parameters from the posterior distribution and latent variables from their posterior distribution and missing data. And you can actually get plausible values for continuous and categorical latent variables. Again, this is part of this data imputation command. You have two useful options here to save the plausible values. The first command, save, basically gives a name of the files that are going to be saved and a star symbol. .dat, and basically what the star means that if you've actually requested, there's another command called n datasets, basically, and that command will determine how many imputations to be performed. So if you want 100 imputations, you will get, you just have to say n datasets equals 100, and basically what this is going to save is going to save 100 datasets where all datasets will contain the imputed value for every latent variable, together with the observed data. So you're going to, this star basically will mean that you're going to get imp1.dat, imp2.dat, and so on. So you're going to get basically 100 separate files, and each file is going to contain the imputed value for every variable. And you can use then these files to actually produce the entire posterior distributions for the latent variables. You shouldn't use it to produce means and standard errors. You should use this option to use to get. So if this option is plausible equals, actually will produce the summaries for the latent variables. So it will produce mode, mean, and standard errors and confidence intervals for every random effect. So I think somebody asked a question earlier about how to get the equivalent of factor scores in the Bayesian framework come from this file. When you ask for this file, you will get the posterior mean, posterior modes, and standard errors and confidence intervals for all the random effects.
All the random effects for each person.
Yes, for every person.
Distribution for each person.
That's right. And basically, we want to feature two separate applications of plausible values. The first one is when you're interested in an individual plausible value. So for a particular individual, you want to know the random effect. That's the first use. And that, to actually get accurate results here, you will have to work with something like 100 imputations, at least. Because you want, if you use the individual plausible values, you need at least 100 imputations. If you're actually going to use the plausible values in a secondary analysis, such as including them in another model, then this essentially treats this another. You have to put your mind in a different framework. You can think of these plausible values and the latent variables as variables that are always missing, and the plausible values as their imputed values. So multiple imputations would always works very well with just 5 imputations. So if you want to actually impute the data, generally speaking, if you want to impute data, you don't need more than 5 imputed data sets. Very rarely have we seen, we've seen some in some cases that you need more than 5 imputations for missing data. So again, the two uses here. One of them, you want to actually get the individual result for each individual, for the random effect for each individual. And in this case, you need 100 imputations. If you're going to use the plausible values for a secondary analysis in a secondary model, then you only need 5. Again, the reason you only need 5 is the multiple imputation theory that says that with 5 observations you can get accurate results. Again, let me just one more thought here. Why can you just do this one only with 5? Because when you do secondary analysis, you get parameter estimates that are representative for the entire population. So any variation within, even though these 5 plausible values that you use for each individual are not as accurate on average, because you use the entire data set and you get you estimate one parameter for representative for the entire population, it actually is okay to just use 5 imputed data sets. That's a little bit of the reason. But the important thing is to understand not to mix them up, right? If you want to estimate for a particular random effect for a particular individual, make sure you get 100 imputed data sets before you use that value. Okay, so some of the good stuff now. Now I have to convince you that why plausible values are so important, because they're much better than factor scores. And here's I'm going to show you this example that's from this technical report on our website. And we're going to basically look at this simulated data set. We're going to look at a one factor model with 3 indicators and a small sample size. 45 observations with indicator reliability of 0.5. And that example is on our website too, if you want to look at it more carefully. So we estimate this with the ML estimator and also the Bayes estimator. The parameters are not that different overall. They're very similar, maybe with the exception of this parameter here. And what is specific for this problem, for this particular example, is that you have a small residual variance. And if you can imagine what happens with the maximum likelihood estimation, when you get this value, small value, think about the model. What the model says is that the factor is really highly correlated with the third indicator variable. So think about this for a second. If you have very, very tiny residual variance in a factor model, what that means is basically that one of your variable, that indicator variable, is really tightly correlated with the factor. And that causes problems for ML. Where here, this is not even a fixed parameter, and it's not even close to 0. So the other problem, in general, is that ML, if this actually came out negative, which often would actually come out negative, you can't even get factor scores. But that's not as dangerous because you don't get factor scores. This is more dangerous because you got factor scores, and if you use ML, you will be using something that's not good. So here is how we actually figure out that ML factor score estimates are bad. basically because it's a simulated study, I know the true factors, the true factor values, and we can basically look at this, the mean squared error. So the difference between the estimated value minus the true value, and here the result. So you get the mean squared error for ML 0.36, and it's much smaller for Bayes. Okay.
Do you want to say how eta hat is created?
Okay, so eta hat, this is for both estimators, and in ML this is basically the posterior mean, and it's essentially a linear combination of the three indicators. In Bayes, we ask for 5,000 imputations, and this is basically the average. For each individual, you get the average. So it's the posterior, again, it's the posterior mean in the Bayesian framework. And let's see what happens to the coverage. Mplus will compute, in both versions, will compute standard errors for these estimates. And the coverage for ML is 20% only. And for Bayes, it's 89%, which is close to the 95% rate. So, so I hope this is convincing enough that you should be really careful with the factor scores in ML, and that Bayes has the solution to that problem. So, one more issue that comes that you can actually see with this example is that the fact that in ML, at least what Mplus does right now is that it produces standard errors, and those standard errors come out of simply looking at the posterior distribution, and those standard errors will be fixed. They're the same across individuals. So it's these are very old formulas, like probably 30 or 40 years old formulas that actually show that the standard errors, if in the ML framework, the standard errors are independent of the standard errors for the factor scores do not depend on the observation. They're constant the whole entire data set. Now, if you actually look at the linear combination with, it is possible to improve on the ML method to actually produce standard errors that vary also there, but at least it's not done in Mplus right now. Anyway, in Mplus, what Mplus will compute is standard errors that are constant across individual. On the other hand, that's not the case in Bayes. Bayes will produce individually specific distributions, and what happens is that observations that are in the tails of so if you look at the correlation between the absolute value of the factor score and the standard error, you get a correlation in Bayes of 0.76. So there's a very high correlation between the standard error and the absolute value of the factor score, meaning that for larger factor scores, by absolute value, you're going to have larger error, which is kind of a natural and justified thing to do, because for larger factor scores, you have less observations because they're in the tail. There are less observations there. So it makes a lot of sense. In contrast, ML produces constant standard errors for all the factor scores, and that's why it misses a lot of the true values on the coverage. So,
and another advantage for Bayes here, relative to the beta blocker example, is that for each individual, you get the distribution, posterior distribution for that person's factor score on that factor. So you can, in the beta blocker case, you actually find that, as Gelman writes, a skewed distribution. So you're more likely to have values in that part than not in the tail part.
So you can have a distribution for a person's factor score, which gives you more information than you've ever had.
Right. So we talked about the ability of Bayes to handle non-normal distributions, and when the sample size increases, all these parameters tend to become normal, and they smooth out a little bit. Not the case for the factor scores, because factor scores are based on the number of variables for a particular individual, which could be as low as 3 if it's a 3 factor model with 3 indicators, and if you have only 3 observations, very likely you have skew distributions. Right, let's see. Okay, here's another example. So I talked about the 2 uses of plausible values. And we discussed the first example, which was basically on the individual level, where you actually look at the actual, Bayesian factor scores. Here's another example of the second type, which is secondary use of plausible values. And this is also in the technical report. And we generated data with a sample size of 10,000 using a model with 2 factors and with 3 indicators each. And for, again, here because this is going to be a secondary analysis of the plausible values, we only use 5 imputations. An ML, again, will use this linear combination of the observed data. And what is the secondary analysis here that we're going to conduct is basically using these factor scores, Bayes factor scores or ML factor scores, to compute the sampling distribution. So we have 2 factors. This is supposed to be alpha 2 here. Alpha 1 and alpha 2 are the means. So basically, you have all the factor score. You average them to compute the sample mean. And by the model, those are supposed to be 0, right? And the sample values are 0 again. And these are well-known facts, by the way, that I'm presenting here. But what it's not well-known, I think, is the fact that the Bayes actually solved this problem. So if you actually use the ML factor scores, the true variance value for the factor score is 1. When you actually compute the sample variance of these factor scores, it's underestimated by a lot. So the true value is 1. Here, if you actually compute the sample variance of the factor scores, the ML factor scores, you get 0.76. So that's meaning that ML factor scores are not a good representative for the population. They underestimate the variance by a lot. On the other hand, the plausible values are pretty much on the mark. Same thing with the correlation here. The true value 0.6. The ML factor scores give you a value of 0.73, which is quite off, while the Bayesian factor scores, which we call the plausible values, actually gives you an accurate estimate. So the conclusion here is basically that if you're going to use these factor score estimates in a consecutive, in another model, you want to use them somewhere else, you better use the Bayesian method and use plausible values, because the results are the much better representation of the factors.
And just to add to that,
in that plausible value report that Timo referred to, our report, there are references not only to Bob Mislevy's work, the plausible values used in NAPE, the assessment, but also Matthias von Davier at ETS has written a sort of a pedagogical description of how to think about and how to work with plausible values, secondary analysis. So there are a lot of interesting things to learn about that topic that I think is worthwhile to try to learn.
All right. So back to multiple imputation, just a little summary of what Mplus capabilities are. And what we found, our experience with users and customer support is that a very basic misunderstanding happens right here, explaining what are the Mplus capabilities. So I'm going to go through this diagram. So when you decide to do imputation, you have to, the first thing you decide is on the imputation model. Are you going to use an unrestricted model, H1 model, or will you use a specific restricted model? So if you decide to use a restricted model, you actually have to include the model in your input, and basically you have to say estimate equals Bayes. And again, what's going to happen here is that particular model that you put in the input is going to be estimated. After the estimation, we'll continue to draw until we get enough imputations. So that's one branch, one possibility to do imputations in Mplus. The second one is this branch. When you decide that you're going to use a saturated model for the imputation, then you have to decide what you're going to do with the data, the imputed data. Do you want to analyze it right away, or do you want to just save it and do analysis later on with a separate run? So if you want to analyze it right away, basically what you have to do another model command, and in that model command you have to specify the model that you want to use for the analysis. And you have to specify an estimator to be used for that imputed data set. And what's very important here that you should not specify estimator equals base. You have to use an estimator that's because what's going to happen, you're going to go in this branch, right? If you specify estimator equals base, you're going to end up here by mistake. So that's important to understand this. This branch is really nice because it actually gives you a simple way to basically, in one run, in one Mplus run, not only will you impute the data, you actually also analyze it, get your results from the imputed data, and everything comes out with a simple, basically, data imputation statement that you add to your input. Okay, and finally, the third approach to multiple imputation in Mplus is that you decide to use a saturated model, and you're just going to save the data. So that's what most programs do, really. Most imputation programs, that's what they're going to do, just here. And that's a simple approach. You just say type equals basic. You specify, the name of the files, how you want them saved, and you have to add again the data imputation statement to say how the data should be imputed. And in this first run, you're going to stop here. If you want to analyze the data later on, you make a second input file that basically is going to use this command as part of the data command, type equals imputation, and there you're going to specify data equals this, data equals this thing with list here instead of star, and that file actually contains the names of all the files.
We'll show an example.
Yeah, we'll show later on an example. But the important thing is that you really need to be clear about these three boxes and know where you are and make sure you're doing what you want to do. So, so far we found that there's some confusion about what's being done. Okay, so now we again with customer support so far the program has been out for about 1.5 years. I guess we've some of these imputation problems are really difficult for us to figure out. So like it could if the data set has 100 variables and there's a convergence problems and you have 5,000 parameters and one of the parameters doesn't converge, digging out for that parameter and the reason why it doesn't converge, it could be very painful. So and again, Mplus will not let you impute unless you have a converging model. So there could be a lot of problems if you start imputing from a model that hasn't converged. You could be getting junk. So we won't let you do that. So that we're like, for example, SAS would let you do that. So and actually probably most programs, you can actually convince most imputations programs to actually start imputing right away. They don't have burning phase. They just give you something that maybe you can hope that it's okay. So in this technical report, after working with a lot of the customer problems that we run into, we actually compiled a long list of 14 tips, so 14 problems that usually occur. And you can look at the rest of them, but I'll just mention the top few. Before you start an imputation, just use some kind of a summary statistics analysis. Like, for example, if you just say type equals basic and nothing else in your data set, Mplus will go and compute like means and standard and sample variance. You can sort of see some things, at least. For example, if you have two variables that are identical for some reason that appeared in the data set, that's going to cause huge problems in the imputation because it can't work with correlated variables like that. So just cleaning up the data set is the first step, I guess, before the imputation. And you can also type equals basic, analyze the categorical data as such. And if the data is Twolevel, you can also just try type equals basic Twolevel, just to get a feel for your data. Then the most common problem is probably this one. So what happens is if you have fully correlated variables in your data set, while this problem is actually okay to work with, now, if you actually put this in another problem that doesn't check the convergence, the imputed data sets, the imputed values actually could be okay, even though Mplus won't converge. But we don't know why the Mplus didn't converge. Okay, but anyway, so here, what is the problem here? If you have dummy variables, and the dummy variables add up to 1, if you have variables that are, for example, indicating one of multiple groups, and for each individual, only one of these dummy variables is 1, and the rest of them are 0. Naturally, when you sum them up, they're going to become a constant. So basically, what you need to do is remove the last one, right? If you dummy variables, you wouldn't put all of them in a regression analysis because again, that you have a dependency between the covariates that basically is going to make your model unidentified. So the same problem happens here. If you have dummy variables in your data set, you have to remove one of them. Another case is when you have like scores, certain scores, and then you have the total of the score. So again, the total of the score doesn't carry any information. Don't put it in the imputation. It's already in the individual scores are already giving you all the information that's there, and that will prevent other convergence problems. Okay, let's see. What is the tip? Another tip is that basically it's amazing to me that very advanced users actually don't know about this command. So you have the names command, which lists all the variables in the data set. And then with this command specifies a subset of the data to be analyzed. So you don't need to create a new data set to just work with some of the variables. So you use this command, use variables, and you list all the variables that you want in the analysis. And that can actually help with imputation as well. If you have a huge data set and just you decide which variables may be related to the missing data, you list them on that command, and that will make the problem much more feasible. And finally, sometimes you basically have these, variables in your data set, such as social security, and naturally, social security has no influence on missing data, and it's a huge variable that it's a large magnitude, and it can cause all kinds of problems in terms of estimating the scale and things like that. So make sure you don't put this into the program. Or a zip code, for example. When a zip code is in there, you can use zip code as a dummy variable. If you transform it as a dummy variable, and that indicates neighborhoods, that's okay. But don't use zip code as a continuous variable because increasing the zip code doesn't really relate to anything.
And Tiamat can't handle it anymore.
Yes, I think I don't know what I'm going to do next time I see zip codes in imputations. Anyway, this slide is just again to mention that we won't impute anything that hasn't converged, even though sometimes it's okay to actually impute from non-converging model. We're not sure why the model hasn't converged, so we won't impute, and you need to figure out the non-convergence and to guarantee that the imputation has gone well. And the other problem is that slow mixing. Slow mixing, it could be also not just non-convergence, but slow mixing, and that could be related, for example, to say if you have a dummy variable that has maybe all zeros except in 2 places it has 1s. Now, this variable naturally has very solid information in there. That the only thing it does actually is makes the whole process, the mixing process might actually be just slow because of that particular variable. So eliminating variables that don't seem to contain much information is a good.
So I'll relieve you for a while.
Okay. In time. Okay, here you go.
So the lesson is we won't impute if it doesn't compute. You have to introduce rhymes towards the afternoon. Learning rhymes. Okay. So now my task is to reinforce what Tiamat just said. So the pedagogical way to do that is to go back to this slide and say that now we're going to do the leftmost branch. The leftmost branch. Okay? And we're going to take a very simple example with lots of comments, bringing it all down to earth, easy to understand. We do H1 imputation without further analysis. And as Timur said, in the variable command, the names option specifies all the variables in the data set. You do not want to use all of them in your analysis or in imputation. In fact, here, use variables is what Timur emphasized we should use more often than we have. That is, only take a subset of all of the variables that we have in the data sets. Those are the variables that will be used to create the imputed data sets. So we assume that those variables have information relevant to the missing data. And there are not that many variables that you can come up with that correlate to any important degree with missing data. Now you may say, so we're going to do imputation based on these use variables, but we have some variables sitting in the data set that we would like to carry with us and placed into that imputed data set. Well, those variables you should put on the auxiliary list. They're auxiliary, they're not part of the imputation at all. They're just hanger-oners, and that we will tack on to the data at the end. So don't leave out use variables, and don't hesitate to use auxiliary. Is one lesson. And on the next slide, in the data imputation, we will specify in the impute option the variables for which missing data will be imputed. On the use variable list, we may not have missing data on all the variables, or we may not want to impute missing data for some variables. So here we specifically specify which variables we do want to make imputations for. And here we also have the chance of specifying that certain variables, like x1 in this case, x1 is categorical. So our imputation method should take that into account and not produce continuous scores. And here's the n data sets. Here we impute 10 times. Like Timur said, typically 5 is sufficient. And then finally, if you put the two slides together, you will then see that the following data sets that we save in the save data list of data sets will contain data for the variables x1, x2. That is, all of these variables that we imputed for, plus z and v. And what were z and v then? Where z was variables that we used for the imputation, but we didn't impute anything for them. Perhaps they didn't have missing data. And v were the auxiliary variables. So those two slides are really important to study carefully. We imputed for the first 6. We used an additional 5 for the imputation. We save an additional 10 just hanging on as auxiliary variables that don't play any role in there at all. And note that we don't say any estimator equals, because that can get us in trouble. And it behooves us to ask for type equals basic to see what kind of sample statistics we get out of that exercise. So unfortunately, in the user's guide, example 11.5 is a less pedagogical version of these two slides. The next version, we're going to make it clear. Things went a little fast there at one point. Now, let's go back to 184. Now we're going to take the path down here. Save and analyze in one single step. So that's very easy as well. Here, well actually, sorry, I was wrong. We got to be really careful here. Go back. We're still in the leftmost track. But we're now going to do save, and in the next step we're going to use the data with type equals imputation. So it's actually the first and the second step in the leftmost track that I want to illustrate. So we have the data imputation command, which says that we want to impute for these variables, and how do we impute? Well, we impute by using the variables on the use variable list. And here's where the misunderstanding came about, I think. The use variable list is the same as the names equals list if you don't say if you don't give the use variables. So then you take all of the variables in the data set, which was fine for this simple little example. But in real analysis, the names equal list is all the variables in the data sets, which are way too many. You should have a use variable list subset here, which you use for the imputation of these variables here. But anyway, we save 10 data sets here. We say nothing about type equals, nothing about estimators here, and we say type equals basic here. So that's the first step of the leftmost track. Now we want to use these variables that we've made imputations for in the linear growth model. How do you do that? Well, in the data command, you say type equals imputation, and the file name is imp, and instead of star, you say list here. Say list, and then you're going to use all of those different data sets that you imputed. And then names, use variables, and model as usual, a growth model in this case, with estimator equals ML. So you impute, perhaps based on a larger data set, larger set of variables. In this case it is, right? We don't use a Z in the model. Z is not in the model. It was only used in the imputations. Let's check. Is that right? Z is used in the imputation because it's included in what will be the use variable list, which is the full list. Z is used in the imputation. Nothing needs to be imputed for Z, but it's not used in the model. So there is the fine feature of Bayesian imputation that you can impute based on, you can have a larger set of variables used for the imputation than variables that you use in the analysis. So estimator equals ML here can draw on information from the Z variable in how the data sets have been generated. Alternatively, like Timur said, you can have auxiliary Z in the ML estimator context, and I think asymptotically these two approaches are equivalent. You can check. There are papers to be written there. Now, let's move over one step here. Let's go down this track. So impute and analyze in one single step. And I think we're on slide 192. Okay, so we input for H1 multiple imputation with further H0 analysis. So we impute for these variables, save them there, and then we say we want two-level analysis and estimator equals ML. So what Mplus is going to do here is to do two-level H1 imputation and then estimate by maximum likelihood. And here is a model, a two-level model, H0 model, which is estimated by maximum likelihood. Did I say that right? Wow. So with that, I'm giving Timur a breather, and he is back.
All right. So actually, this next example that I'm going to present is actually kind of a little bit of the flagship of this imputation business. So that's really kind of one of the big breakthrough for us. So I mentioned it already. So basically, you have with categorical data, you have factors, random effect, and if you have many of these, ML is intractable. So the only one that's feasible is the weighted least squares, except weighted least squares cannot handle missing at random very well. So now we basically have a new good alternative, which is multiple imputation followed by weighted least squares. And a very simple example to convince you in that, we conduct a simulation study. Actually, can I ask you another question? Who has used the model of missing in Mplus? You guys know what model of missing is? So basically, that's a very useful thing to know and understand and play with it, because I think it will let you understand what exactly MAR means. So MAR, missing completely at random, basically there's a way to actually write. So basically, model missing it tells you how to generate missing data. It's a Monte Carlo feature, and it gives you a model. It's basically the model that decides whether observation will be removed as missing or it will stay there. And the three types of missing data that we talked about, missing completely at random, missing at random, and missing not at random, can be generated in Mplus, and you can see the effect of this type of missingness. So anyway, here, this Monte Carlo study basically is a simple growth model, linear growth model with 5 time points, binary outcomes, sample size of 1,000, MAR missingness. Basically, the missing data is a function of the first outcome. So the first outcome is 0 or 1. The rate of missingness for if it's 0 is 1, and if it's 1, the rate of missingness is different. Basically, the likelihood, the probability that an observation is going to be missing depends on the value, the first value that you observe. So it's going to be different probability whether it's 1 or 0. So that is a simple way to generate MAR missing data. So we actually varied the number of imputations from 5 to 50. We used the non-restricted imputation using the sequential model. And that's again in that imputation paper. And let's see the results. Very convincing. Weighted least squares, huge bias, low coverage, weighted least squares with 5 imputation, perfect coverage, low bias. Weighted least squares with 50 imputations, not different. So 5 imputation is enough. And basically, these slides basically tells you the true values here, and basically the means of the random effects and the variance covariance matrix. But bottom line is, if you have missing data in using weighted least squares, think about using imputations. It's a simple way to go about it, and very good. Okay, so we're going to move to the next example, and that's an example of H0 imputation. And here we have a multiple time points growth model. That's the model here. I'm going to go through the input. And you have the 9 categorical variables, these 9 variables. And we're going to do an H0 imputation, so we're going to have to write the model. This same model has to go into the input file. So here's the model. You have the factor measurement model. Again, all these basically parameters, and 1 through 2 are basically the names of the parameters, and basically this indicates that the loadings are held equal. The thresholds, these are the threshold parameters, they're held equal across time. And you have the growth model statement. And again, to do the H0 imputation, you need to add this data imputation statement. That's all you really need to say to get the imputation going. And you specify the number of data sets to be generated. Again, the plausible command is going to give you the file with all the factor scores, the average plausible values. And this also is going to generate the data files with all the plausible values.
So here factor scores will be not only F1, F2, F3, but also I and S.
Yes, that's right. Okay, here's a two-level imputation example. And again, in two-level imputation, what you can run you can run very often into a problem that on the between level, if you've run two-level structural equation models, you know that on the between level, everything becomes really highly correlated. So just because of this problem, you may not be able to estimate an unrestricted imputation. the variance covariance matrix on the between level may be singular. The between components of these variables may be highly correlated in a large two-level imputation. And so, in this case, what we recommend is just doing a one-factor analysis model on the between level. It's a very simple model, and it will capture basically a large portion of the data, because it will get the majority of the main portion of the correlation, and it's easy to estimate. And so we're going to actually, what we're going to do in this example is basically conduct the H0 imputation. We sort of pretend we had a problem with the H1 imputation here, and we're conducting H0 imputation with a one-factor analysis on the between level. So again, this is basically listing the variables. In two-level, you have to specify the cluster variable as well, and we're going to do H0 imputation, and we have to specify this estimator equals base. And here, basically, the command lines for specifying the factor model on the within level. So you have the 3 factors and the 3 measurement models here, and the 1-factor model on the between level. And again, you have the data imputation command. Okay, so this statement actually is important. I'm not sure if Bengt actually mentioned already this or not, but basically you can see that there's a C here. So, okay, I guess, does anybody know what the C stands for? Okay, so I guess Bengt said it already. Yeah, so if you don't say that, you end up with imputation that you're going to have categorical data. You're going to expect categorical data. Instead, you're going to get imputed values that are not categorical. So you have to have this to actually get categorical imputed values. Once you say it, if the data has 0 and 1s, the imputed values are going to be 0 and 1s, and they're going to be imputed from the data from this model for the categorical data. So okay, so and again, it's the saved data file that saves the imputation. Okay, and now once you've imputed the data, you can analyze it with something a little more complicated, because again, it's the imputed imputation data might be a little tricky to estimate. So, but the estimation model with you can use the weighted least squares to estimate this model, and weighted least squares is fairly robust, so you won't have any problems. And basically, again, what is the command that we want to look at this? Now you've generated 5 data sets. Actually, were they 20? I think there were 20 actually. No. Oh, okay. When it doesn't say how many to generate, it uses 5. That's our default. So if you don't mention n data sets, the number of data sets to generate, you get 5. And so basically, in a second run, so you've generated the data set. In a second run, you want to use the weighted least squares to analyze this imputed data sets. And basically, what you have to say here is specify this list command. When you actually get the imputed data set, you get you get the 5 imputed data sets plus a separate file that contains the name of these 5 data sets. And when you actually want to analyze, you say this file. It's basically the same name that you used before with the star symbol, except it has list. So that file again has 5 rows. In these 5 rows are basically the name of the files for the imputation. And you say this type equals imputation, so we know that there are going to be multiple data sets into this analysis, and they have to be summarized according to the Rubin's formula for multiple imputation analysis. Okay, so again, you have weighted least squares. You have to specify the clustering variable. And here again, the statements for the factor analysis, 3 factors, a growth model on the within level. And the same thing on the between level. 3 factors on the between level and growth model on the between level. Okay, so here's another important thing. The safe SW matrix. Do you guys know what that is in Mplus? Anybody knows what the SW matrix is? Okay, I think only one person. Anybody else? Okay, so SW matrix, when you run two-level analysis with weighted least squares, there is a pre-processing that goes on in Mplus. It basically goes through estimating all the sample statistics, two-level sample statistics, meaning thresholds, within-level correlations, between-level correlations, and this, because if you have a lot of variables, that actually can be a time-consuming process. Weighted least square is a fairly fast estimator, but just summarizing these sample statistics actually can take a long time, and this actually is independent of the model. So you actually can do it once. And to avoid doing it multiple times, we have this command, which basically would store these sample statistics and all the metrics that are needed to analyze different modes after that. So that SW matrix has two versions. One of them is in the save data command, and then the second version is here. And the second version is in the analysis command when you want to use it. So anyway, and then basically this also works in multiple imputations. Are we running out of time, or?
No, I just want to emphasize a point
Okay.
that you made that I think is important to hear
Twice. So Tiemer made an important point here that when you have two-level data and you want to do imputation, the H1 model can be very difficult to work with. It may not converge. The H1 model may not converge, so you cannot impute, for the reason that between-level variables correlate very highly. So what do? Well, we choose an H0 model, and in particular, we try to make it H0 for the between part, simplifying the between part. And it's interesting that this is the model that we're after on the between, a growth model. See those 5 circles there? Note that we didn't impute according to that. We imputed according to a simpler model. This is our imputation model, 1 factor on between instead of 3 time point factors, a growth model. So this imputation model is actually then wrong in some sense, right? If you believe in the analysis model. But it's not wrong in a too bad of a way. It's good enough. And one interesting research question, there's so many research papers, methods papers available to write here, is how wrong can you be in the imputation part without the analysis model results being distorted? And I would note that we only use this model to get the missing values. Hopefully we have many, many more, higher percentage of non-missing values. But it's an interesting question, how simple can you be here without distorting the results from this analysis model? And it comes in, for instance, if you do growth mixture modeling, can you impute according to a single class model if you want to then analyze by a mixture model? We don't know the answer yet. I'm trying to make it a little dramatic here. So Tiemer, here.
Okay, I think this is maybe the last thing that we're going to. Okay, so just technical aspects of analyzing multiple imputed data. This is like a very standard formula, actually. If you type in Google multiple imputations, then you go to this web page by Schaefer, and you get all these formulas. So how the